Heller will tell us about complexity, conformal field theory. Please, 45 minutes.
Hello, everybody. Thanks for joining. Thanks, Irina and the organizers for putting this together. I must say, I'm really sad that that the conference didn't happen really in Moscow. But on the other hand, I think doing this virtually is a great idea, and it's certainly better for the environment in the grand scheme of things. What I want to tell you about today, and I hope you can see my screen and hear me well, is a talk eventually about the paper with Mario Flori, who's somewhere there in the audience, on complexity and conformal field theory. So this is a broad topic of research with many recent works at the intersection of holography, so quantum gravity and quantum field theory, as well as quantum information science. So basically the topic of this virtual conference. And I wouldn't be really giving a presentation about it if not a discovery or an observation dating back to 2014 by Lenny Susskind and later works by many people, including many people around Susskind at Stanford. And this is the discovery or observation that there are some novel observables in holo ADS, anti-de Sitter quantum gravity that deserve attention, and conjecturing at the same time that these observables might concern the notion, quantum information theoretic notion of complexity in the dual description, hence the name holographic complexity proposal. Although I won't be really talking about them in any great detail, let me present them for completeness and for you to understand why they are interesting. So let me start with the vacuum ADS solution. Over here in my transparencies, I'm trying to use my cursor as a pointer. You can see ADS3 basically. There's a time direction, there's a boundary, and there's the interior of the cylinder, which is the holographic ADS3 geometry. And now let's imagine that on the boundary, we pick a time slice. So this is a time slice on the boundary, this dashed curve. And this time slice in the quantum field theory, this is a two-dimensional conformal field theory in this case, defines for us a state. And this state we can characterize in many ways. We can calculate expectation values of various observables. We can calculate entanglement entropy. But anyway, the idea is that what we can do is we can take our ADS solution that fills in this Lorentzian cylinder in which our holographic conformal field theory lives, and we can define two sorts of gravitational observables that are covariant, that is, that are entirely defined in terms of the curves on the boundary. So one observable that you can do is to consider a volume of a codimension 1 slice in the bulk of ADS that is anchored on the boundary on a given time slice. And this is, there are many set volumes. So you need to have an additional condition to specify which one you talk about. And a nice condition, probably the only one that makes sense in the Lorentzian case, is to talk about the maximum volume time slices. And maximal volume time slice is unique, and this is this orange object over here. And then what you can do is you can compute its volume, and then you can wonder what this volume corresponds to in a dual conformal field theory. And the only thing that we can say at this level is that this volume presumably reflects some properties of the underlying state that is defined by picking this time slice. So that's one codimension 1 observable, quantum gravity observable that one can consider. And the other one that one can do is to consider an object that's going to be codimension 0. And this object is defined by taking a time slice on the boundary and shooting to the future and to the past line rays This light ray is defined as causal diamond that is depicted, or the boundary of which is depicted here with blue. And then what you can do is you can evaluate the gravitational action inside this causal diamond, or you can evaluate its volume. And this is another possibility. I mean, this is another quantity that is interesting. It's kind of novel because it's not codimension 2 as entropies that people talk predominantly about in quantum gravity till 2014, but it's actually codimension. These are codimension 1 and codimension 0 quantities. And you might wonder what they really correspond to in dual quantum field theory. The story gets even more interesting in the context of black hole solutions. So over here, I'm drawing for you an eternal, so maximally extended ADS-Schwarzschild solution. And this solution has actually 2 times on 2 asymptotic regions. So picking a time slice requires picking basically a time on the one boundary and on the other asymptotic region. And then we can play the same game in a sense that we can construct similarly to here, we can construct codimension 1 maximal volume slice and evaluate its volume, or we can construct this causal diamond. And then we can probe the properties of these objects. I mean, this is a subject of many, many works. And wonder what these quantities really correspond to in a dual quantum field theory. And then, of course, the conjecture is that they correspond to complexity. And if I were to, I didn't really introduce it, I'm going to introduce it in next transparencies, but if I were to provide you with a hand-wavy arguments why this might be correct, one argument would go back to the interpretation of the role of tensor networks in holography. So in particular, if you were to, if you were to consider this time slice as being effectively a mirror type tensor networks, then the volume of this time slice would be like counting tensors in this mirror tensor networks, and then counting tensors is like counting number of operations. And then, as you will see, this complexity is a topic or is a notion related to it. So that's one tangential point why these things are kind of interesting. So the last thing that I want you to take home from this transparency that's going to be relevant for whatever I have to tell you later on is that these holographic complexity proposals, they deal with quantities that are intrinsically divergent. So, and this has to do with the fact that the antidistor space has an asymptotic boundary. This asymptotic boundary is infinitely far away. So when we calculate this volume or when we calculate this action, there's going to be divergences that come from the near boundary region, and that's how it is. It's similar for entanglement entropy, and we learn to live with it. So this is something that is interesting. This is something that appeared in our field in the course of the past 6 years. And the motivating question for whatever I have to tell you next is the question: what holographic complexity proposals stand for in holographic quantum field theories? That's basically the spirit of the rest of the talk. So let me mention that I would like to make this talk as interactive as possible. So if you have some questions, just pop in and interrupt me. I deliberately prepared a small number of slides so that I can be stopped many times and answer questions or listen to comments. So please do so if anything occurs to you. Any questions? So I guess not. Let's continue. So I told you about holographic complexity proposals, and I would say that what we want to do is, or what I want to do now is to present a series of developments that allow you to define the quantity complexity in quantum field theories. And after presenting to you like what's been done in the context of simple, that is, free quantum field theories, I want to eventually discuss developments that have some hope of matching holography in a precise and quantitative way. So let's start with a very simple setup. This is a setup that I discuss very often in my talks on complexity, but it turns out that about a year ago, Brown and Saskind actually wrote a whole paper in which they discuss this setup at an excessive level. So this setup is a simple quantum mechanical system that is a system of one spin. And in this particular setup, what I want to discuss is how to think about complexity that the authors of holographic complexity proposals had in mind when they introduced this subject to our discipline. And complexity is a quantum information notion that concerns the hardness of defining an operator, and this operator basically for all the talk, I'm gonna assume is a unitary operator, or some state, and I'm gonna denote the state target state, hence T, from what one considers a simpler state using a restricted set of resources. So for definiteness, let's come back to this simple single spin model. And let's imagine that somebody wants us to realize a unitary transformation in which we rotate the spin pointing along the x direction to be a spin pointing along the z direction. So our reference state is going to be this one, our target state is going to be this one, and the sphere over here is nothing else than the block sphere. So one way to achieve it, perhaps like the most obvious one that would occur to you, is to perform simply a rotation along the y-axis by an angle, with an angle pi half. But that's obviously not the only way to do this. There are infinitely many other ways of doing this. And one such way would be to, say, first rotate along the z-axis so that our spin starts pointing along the y direction, and then performing an additional rotation also by pi half along the x-axis, right? That would be another way of achieving the same task. And I'm saying this because you see that all these transformations are generated by Pauli matrices. And if you were to quantify the cost of doing these transformations, then perhaps the thing that is the most natural at this level is basically the angle by which we rotate it. And over here, we rotated once by an angle pi half. In this example, we rotated twice by an angle pi half. This is the first rotation, this is the other rotation. And naively, you would say that this example is simpler. It involves only one rotation by a given angle. This example is more complicated because it involves two rotations by this angle. And well, this very naive intuition can be summarized by the statement that pi half clearly is smaller than pi half plus pi half. Now, basically, the notion of complexity that I want to introduce is going to be a notion that's going to be basically minimizing, in this example, the total angle over which I had to rotate. But the beauty of this quantity is that it's entirely up to us to discuss what's hard and what's easy. In a sense that we can imagine that rotation, for some reason maybe related to the experimental realization of our single spin, single qubit system, the rotation along the y direction is 10 times harder to do than the rotation along the remaining directions. And as a result, if we want to quantify it, what we can do is we can say that, well, the distance traversed in the y direction, we're going to multiply by the penalty factor of 10. And the distance traversed in the other directions, angular directions, we're going to leave unmodified. We're going to count with a multiplicative factor of 1. And as a result, you see that suddenly this rotation, this composite rotation, becomes cheaper than the single rotation. So this is basically the background, the simplest example that at least I could think of in which one can discuss a more general structure. And this more general structure actually was outlined by quantum information scientist Michael Nielsen in a series of papers that start with this one in 2005. And his collaborators' later idea was to come up with an approach in which one can basically bound the number of elementary discrete quantum computing gates using continuous transformations, like here in a multi-qubit system. So now let's try to take this single qubit example and let's try to make it a bit more abstract. So this unitary transformation that was achieving a task for us, so here rotation, can be thought of as a path order exponential, in which what we do is we're evolving our system with some potentially time-dependent Hamiltonian. And this time-dependent Hamiltonian, I'm gonna call Q of tau. And this tau, I refer to it as time, but a priori it has nothing to do with physical time. It's just an auxiliary parameter that tells us how our operation is divided into a sequence of smaller operations. And now each smaller operation, so an operation occurring at one layer of the circuit, I'm gonna divide into a sum of some generators. So over here, the sum of generators is gonna be basically sum over Pauli matrices. And basically number of times each Pauli matrix, in this case, was applied in each layer of the circuit. And I can think about this object, this epsilon I, so I is an index over here. This index is gonna run from X to Z, right, like 3 Pauli matrices. I can think of this object as an abstract vector, here vector with 3 entries. And now what I can do is I can introduce norms that calculate the length of this vector. So one norm would be like to add absolute values of the component in the X direction plus absolute value of the component in the Y direction, absolute value of the component in the Z direction, right? So that's going to be a contribution from one layer, and then integrate over all layers, right? And then this basically would be a cost of doing some transformation. And now what you want to do is you want to minimize this cost over all possible transformations that take us from, in this case, a reference state to a target state, or that generate for us unitary starting from identity and ending up with some desired unitary, for example, the rotation along the Y direction. Now, in this more abstract expression, what I also introduced these penalty factors. So these pi I in this context are just non-negative numbers that tell us which operations we consider harder and which operations we consider easier. So this is a notion of, so the notion of complexity is based on introducing a cost assigned to a circuit and minimizing this cost subject to initial and final condition that reflect where we're starting from and where do we want to get to. And now there are many different norms that one can consider. One can consider, for example, an L2 norm in which these velocities in the circuit would contract with some non-negative symmetric matrix. And there are also other choices, and some of these other choices you will see later in my talk. And what I want to emphasize is that basically this discussion over here is concerned about the complexity of this unitary transformation, but having a state like here, we can use a complexity defined for a unitary transformation also to define a complexity of states, right? Because we're gonna be looking at all unitary transformations that interpolate between a given reference state and a given target state. So this is basically this example. So it's a good place to stop and ask if there are some basically background questions on this front. Because later on in my talk, I will be using basically all these ideas and notions. Okay, if there are no questions, let me move on. So what I told you about is that if somebody asks us to prepare a unitary, what we can do is we can, and this unitary can be then used to take us from one state to the other. This is a very general procedure, and in order to apply it to some particular to a particular case of interest, what we need to do is we need to identify what we call elementary operations. So in this context, these are some Hermitian operators. And if we want to talk about some particular states, somebody has to tell us like what's the reference state, what's the target state, right? And once we fill in this basically background, then the open question is to be able to do manipulations with this notion, which is to minimize it. And this is far from obvious, and one will be able to minimize it in physically interesting situations. Nevertheless, in some cases, one is able to do so. And the case of interest or like the first case of interest that we consider as a community were free quantum field theories on the lattice. So these were free fermions and free bosons. Over here, my discussion covers basically the free bosonic case. So the important aspect of free theories is that the ground state as well as thermal field double state are Gaussian states, in a sense that these are states that are entirely specified by expectation values of one, by 1 and 2 point functions of fundamental variables. And now, as a result, if you want to talk about state preparation for a free quantum field theory, starting from some simple state, ending with, say, a ground state of this quantum field theory, we can consider this problem as a toy model entirely in the realm of Gaussian states and Gaussian transformations. And these transformations are manageable in a sense that one can use standard results in the literature on Gaussian states from quantum optics and embed them into the problem of finding complexity. So in the context of free quantum field theories, the studies in the literature concern unitary gates that were based on exponentiations of basically phi phi, pi pi, and phi pi on different lattice sites. And upon introducing certain fine-tuned cost functions, which were related to L2 norms, what happens is that one can actually do the minimization problem exactly and get concrete closed form results for complexity. The price that we paid to be able to do the minimization problem is that we were generating ground states of free theories by starting with states that were spatially disentangled, which you can think of as, say, harmonic oscillator at every lattice site in the bosonic case. But in order to be able to do calculations, we couldn't really exclude the use of operators that were very non-local. So we were using operators in which we're acting simultaneously with a field operator here, say in this room, or and the other field operator in Moscow or in other galaxy. So this was something. This was a technical assumption that we had to do. And the last point that I want to outline is that when we talk about these unitary transformations, we didn't really care if this unitary transformation was generating for us any phase. So and the reason why we didn't care about phases is that in the end, phases, like constant phases, are irrelevant in quantum mechanical theories because they cancel in observables, and states are just raising Hilbert space. So U1 phases were completely ignored. We didn't assign any cost to U1 phases because these operations are identity operations that are generated by identity, Hermitian operator identity. So we ignore them. So this is the technical aspect of this construction. And now coming back to features, the good feature of all this, and that's probably why I'm talking about it here, is that it worked in a sense that you can make choices in these calculations that reproduce actually very well static properties of holographic complexity proposals, despite the fact that free quantum field theories obviously are not really holographic. So when you go back to these holographic complexity proposals, I told you that the results were divergent, and you can make choices in these calculations such that you reproduce the leading divergences of the vacuum states in diverse dimensions. When you look at this black hole, problem, you can make choices to reproduce the complexity of this black hole at some fixed time. When you look at subregions, so you do Ryuta-Kanagi related, so you use Ryuta-Kanagi to define complexity for subregions on the boundary. You can use free quantum field theory results to reproduce the features of these calculations. So I mean, they're encouraging. The way I want to treat them are as encouraging hints in the direction that perhaps these holographic complexity proposals are really about complexity. The bad aspect of these calculations is that they were based on Gaussian states. And as we know from other studies in holography, when one compares the results of strongly coupled quantum field theories with results of weakly or even free quantum field theories, when it comes to time dependence, the match is not really very good. It's actually awful. So as a result, when one looks at time-dependent properties of complexity in free quantum field theories, they come out very different, actually, from what one observes in holography. This is expected. This is not something that one should take against these calculations. But what's really problematic, and this is basically the core behind my motivation to talk about the work we did with Mario, is that these calculations do not really generalize to interacting quantum field theories, in a sense that they were really based on the machinery that is only applicable to free quantum fields. So if I were to take a step back at this whole field of research of complexity in quantum field theory, it looks a bit as if these holographic complexity proposals that are denoted by CB and CA are a bit like calculating HRT, so Hubeni-Rangamani Takayanagi surfaces or new Takayanagi surfaces before first works on entanglement entropy in quantum field theory. So quantum field theory happened likely to be a subject that basically started in the 80s and was actually quite well explored at the moment we asked the committee question of what's the interpretation of entanglement entropy in holography. But what's kind of obvious is that history likes to repeat itself, and perhaps one can try to draw a lesson for complexity in quantum field theory that is buried in how the field of entanglement entropy in quantum field theory developed. And if one looks at this, then what one notices is that pioneering works in the 80s, which is this paper by Bombelli and collaborators in the early 90s, they looked actually quite a lot like studies of complexity in free quantum field theories. I mean, they are just concerned with, say, free bosons or free fermions on the lattice. But then the thing that really made a difference and led to an exponential progress in understanding complexity entanglement in quantum field theory, it all goes back to the universal result for entanglement entropy for single interval in the vacuum for 1+1 dimensional conformal field theory. And this is this result. It appeared for the first time in a paper by Holtze et al., and later in a more streamlined version in a paper by Cardi and Calabresa. So the idea behind the paper that appeared on the archive today with Mario Flori, and the idea behind this talk, is to take the field of complexity in quantum field theory and work towards what would be a universal result for complexity analogous to this this highlight for entanglement entropy. So this is what I will talk for the rest of my talk. So as I already indicated, this free boson, free fermion approaches, they do cover massless theories in the sense that mass there is a parameter. Mass does not affect if we're talking about Gaussian system or not. But these approaches do not really utilize specifically the structure of conformal field theories. I'm talking about primary fields and so on and so forth. And as I said before, they do not really generalize in any natural way to holographic conformal field theories. And you might say that the agreement with holographic complexity proposals, if holographic complexity proposals are about complexity, might come from some sort of a universality that this quantity sheds, similarly to entanglement entropy. So the approach that I like a lot, actually, and it motivates also partially this work, is the so-called path integral optimization that appeared in 2017 by the Kyoto group, in which one tries to prepare a state in a quantum field theory, not necessarily holographic, by doing Euclidean path integrals with various sources and try to minimize some cost functional with respect to these sources. And it turns out, as we've shown with Hugo Camargo and collaborators, I think Hugo is there in the audience, is that one can think about this approach as a version of circuit complexity, but there's still there remain some significant puzzles, and these puzzles need to be resolved. A similar in-spirit approach is a paper by Belin, Levkovich, and Sarosy, and I think Gabor is also there in the audience, which is also based on quantum field theory sources and state preparation using path integrals, I think mostly Euclidean. So this paper, quite remarkably, was able to reproduce some features of this volume calculations in holography. But I would say that I think it's a fair comment that the CFT understanding of this construction is somewhat limited, and one would like to do better. And I think that the last stimulus for our paper are actually two works. One work that appeared in 2018 by Paul Zaput and Javier Magan, and the paper that appeared by the Würzburg group with Johanna et al., some of whom are here in the audience. In April this year, Johanna talked about it on April 28th on this conference. So these works really provide the setup that we want to address from this grander scheme of trying to advance the field of complexity in conformal field theory in 1+1 dimension. So it's a good place to stop and ask for questions, if any.
Can you mention briefly what puzzles are from the paper about path integral as a circuit complexity?
Okay, so
just briefly.
Yeah, sure. I don't have much time. So the main puzzle there was that we are able to define cost functionals that were reproducing the Liouville action for those of you who know the path integral optimization approach, but only as an approximation and never as an exact statement. And then when one optimized this cost function exactly, one got a priori somewhat different result when one optimizes its approximation, and that was kind of puzzling, and we never really get to think like what was the proper way of thinking about it, and that led us to with Mario to try another direction.
Okay, thank you.
Anything else? Okay, so let me discuss the setup. So the setup is as universal as it can get. So we and we'll really follow these papers. So we wouldn't really be here if not these earlier works. And some of you might be familiar with the setup from Johanna's talk. What we do is we consider a conformal field theory in 2 dimensions on a Lorentzian cylinder, and this Lorentzian cylinder has a spatial coordinate sigma. And what we do is we look at unitary circuits that realize the homomorphism of this spatial circle in a gradual way. So what we want to do is we want to go from sigma to f of sigma not in one big step, but actually as a sequence of steps that are parameterized by the parameter tau, and this tau should ring a bell with being the circuit parameter, such that at tau equals 0 that we chose kind of arbitrarily, we start with f equal to sigma, and at tau equal to 1, we finish with whatever transformation we want to reach. And such circuits are realized by unitary transformations in our conformal field theory that are given by a path order exponential with this q of tau, where q of tau is, I should call it time-dependent Hamiltonian, but of course it's not really precisely the Hamiltonian that we talk about in conformal field theory. This q of tau is nothing else as a smeared, say, right or left moving component of the CFT energy momentum tensor with a particular velocity, and this particular velocity is related in an intricate way to the transformation that to the way we wanted to interpolate between these two transformations, the identity and some non-trivial one. And now, of course, if you look at this expression and go back to this say example where we talk about the Pauli matrices, right? The generators there were Pauli matrices themselves. So over here, the generators, at least superficially, one way of thinking about gates would be as the energy momentum of energy. The component of the energy momentum tensor at a particular position on a circle, right? And the velocities previously were like infinitesimal angles, and now are going to be basically this infinitesimal diffeomorphism. So this is the setup that dates back to these works, and of course, if you dig into the literature, you're going to find it in many other places before. That's my guess. And now, what I want to talk about is directly to pass to this paper that we've written with Mario. Although I must say that the notion that I'm gonna talk about mostly made an appearance in this paper by Javier and Pablo, and this is the Fubini study metric. So the motivation for us to consider Fubini study metric, that is a metric of the Hilbert space of our, in this case, CFT, is that if one wants to match with holography, then it would be ideal to assign cost to circuits in a way that requires minimum of choices. So, for example, if we want to, if we wanted to count insertions of this Pauli matrices in the simple example with spins, there were zillions of choices that we could make how we did the counting. I mean, some of you might remember that I talk about discounting rotations along the X and Y, Z direction with respect to rotations along the Y direction or something like this, right? So there are choices that you can make. And if you count gates in this way, then you're always sensitive to these choices. However, one thing that is very universal is that all these systems that we talk about, they have their own Hilbert space. And one can try to use the distance in Hilbert space to provide us with a cost functional for circuits that we later on can minimize. And this functional is going to be universal because if you know how to calculate overlaps in conformal field theories, and if you know how to calculate overlaps in holography, then in principle, there might be a way of mapping between these two. And I should say that this approach to complexity using Fubini study metric appeared in 2017 in the paper that I wrote with Shira Chapman, Hugo Maraccio, and Fernando Pastavsky. So what's the idea? So the idea is that there is a unitary that we want to realize as a circuit. And we take a state. This state at this level is an auxiliary state, and I'm going to denote it by H. Of course, in the end, this H is going to be the energy eigenstate in our CFT on a circle corresponding to a primary operator of a chiral dimension H. And what we're going to do is we're going to take the circuit and we're going to act on the state. And we're going to cut the circuit at some value of the circuit parameter. And that's what it defines for us is a one parameter family of states in Hilbert space in our quantum field theory. And this one parameter family of states interpolates between the state that, this auxiliary state that we provided, and the final state that is like this final unitary acting on this auxiliary state. But in the middle, like over here, these are some, in principle, other states that we're going to explore as the circuit unfolds. And now the scalar product on the Hilbert space defines for us a distance, and we can calculate this distance that the circuit traverses as a function of the circuit parameter, and take it as a cost function, that is, minimize it with respect to starting at identity and ending with some desired unitary. So what I'm saying is that we're going to take the distance on the Hilbert space, we're going to integrate it over all along the whole circuit and minimize it. And if you do the math correctly, this minimization problem is nothing else than minimizing the variance of the operator that generates layers of the circuit in an instantaneous state that circuit defines. So this is one proposal for a very natural quantity to optimize in any quantum mechanical system, including 1+1 dimensional conformal field theory. And now, if you do the math correctly, this cost functional for a conformal transformation for the diffeomorphism of a circle is going to take the form of basically an expression that contains three integrals. There's an integral over the circuit parameter because we're summing contributions from different layers, as well as there's a contribution from each layer. And this contribution from each layer is nothing else than a 2-point function of the stress tensor in the state H that is weighted with this particular combination. And of course, I mean, this might become a bit technically challenging. The reason is that there's a double integral. Over here, we have high order poles, so one should be careful when working with this expression. It turns out that the method of regularization that is called differential regularization, developed for quantum field theories, works beautifully in this case, in this setup, and we employ it, and we are able to actually use it to find optimal circuits. Now, this is one possibility, and this is the possibility that we mostly looked in to this paper, but there are others. So because we have a Hilbert space and it defines for us distances, one thing that we can do is, instead of calculating the variance of a layer of the circuit in a state that is evolved with our circuit, we can evaluate this variance in the state that we started with, this H. And that's another possibility. And the cost functional actually looks quite similar to the one here, but now instead of the transformation, an inverse transformation appears, right? But the structure of the cost function is quite similar. So these are the setups that we want to or we address in the paper. And in the meantime, the talk managed to get quite technical. But let me try to discuss some virtues of this approach. So the key asset of these cost functions, so you can look here, is that these cost functions have squares of time derivatives. And the fact that the time derivative, so the derivative of this f with respect to the circuit parameter, with respect to this judicial time appears there, is really crucial for us to have a well-posed variational problem between two generic transformations, the transformation that we start with, that we can take to be, for example, identity, and then the transformation that we want our circuit to approximate in the end, that we want to be free to choose. And now, this is actually in contrast with earlier works on the subject, because these earlier works on the subjects focus predominantly not on the variance of the layer of the circuit, but actually on the expectation value of the layer of the circuit. And if one do the math in this case, the resulting cost functional is actually an integral of an expression that is first order in derivative. And this is at least superficially in contrast with the ability of interpolating between two arbitrary conformal transformations. as well as it contains this piece given by the Schwarzschild derivative that is nothing else than related to a U1 phase appearing in our circuit. And as I said before, these U1 phases, at least naturally, I would consider as being trivial transformations that we don't really want to assign complexity to because they are proportional to identity. Now, what's important is that if one looks at such a, what's important is that if one looks at such a cost function, things would be very, very different if over here one would put an absolute value. But without this absolute value, this variational problem seems to trivialize. And what I'm trying to claim is that this Fubini study cost function actually goes around this issue. The other thing that I want to point out is that actually this set of cost functions connects very well to three known integrable PDEs from mathematical physics. This to some degree appeared already in an early paper by the Brisbane group. That's why I'm going to skip it in lieu of time, but you can have a look at one of 2 of our papers. What I want to discuss in the remaining few minutes of my talk are basically the properties of this complexity defined by the Fubini study metric. And the reason why I'm focusing and the paper predominantly focus on this particular case is because it's really interesting. These other, the solution of variational problem for these other cost functions I discussed are solutions of PDEs, and solving PDEs, especially integrable PDEs, is at least possible using Mathematica, and one can also hope to import some knowledge from textbooks that are discussing these PDEs in detail. However, for this Fubini study metric, things are more interesting because, to the best of our knowledge, people have not looked into its minimization in the problem of interest. And this is actually a very interesting problem that represents a geodesic motion in the metric in which indices are continuous parameters and correspond basically to coordinates on the circle. This metric is actually curved, and finding optimal circuits requires solving a geodesic equation in this geometry. And this geodesic equation is actually an integral partial differential equation. So as you can imagine, it's a bit of a mess. However, for a set of diffeomorphisms that are small perturbations of identity that contain only single Fourier modes, so here for definiteness it's sine of sigma, and this amplitude A is much smaller than 1, what we were able to solve these equations of motion interactively in the amplitude. And what we got is, we got that to the first order in this perturbation on top of identity, the circuit, what it does, it interpolates in a linear way between identity and whatever it wants to reach. And now, quite interestingly, this is precisely the result that appeared earlier in a paper by Gabor and collaborators in 2018. And this result actually was seen to agree well with the volume calculation done in an earlier paper by Mario Flori and Nina Mikli. Now, our prediction, sort of like one of the most important results, is that we can actually solve these equations to higher order. And the question is, can one use such an iterative solution in order to seek for the agreement with the complexity equal to volume proposal at a more detailed way? So I have to refer you to the paper for more. We're also able to calculate the sectional curvatures of these geometry, and the conclusion was that in a reasonable situation in which H is not of the order of C or larger, most of the sectional curvatures at identity were negative, which basically means that when we construct our circuits, the solutions, at least initially, want to diverge from each other. So I'm basically out of time. So let me here try to summarize what I said in some digestible way. So the idea for the present talk was that conformal field theories in 1+1 dimension provide an invaluable lab for understanding complexity beyond 3 quantum field theories in a way that might ultimately allow to make contact with holography. So several approaches already appeared today. One of them was the work on path integral optimization. The other ones were about earlier attempts to count gates in conformal field theories. Yet another ones were trying to look at these binary geometries and try to evaluate holographic complexity proposals there. So in a paper that appeared today on the archive that we've written together with Mario Flori, we introduced and explored a notion of complexity for 1+1 dimensional conformal field theory that was based on looking at circuits involving only exponentiation of the energy momentum tensor, actually one component of it. And the virtue of these complexity functionals were they are nice because they do not assign cost predominantly to U1 factors in our transformation. And they also lead to a well-posed variational problem in which an initial and final condition can be arbitrary. Now, this work is only a step in a bigger scheme of things, in which the ultimate goal would be to try to come up with a more universal understanding, some sort of a universal prediction for complexity in conformal field theories that is based on underlying Virasoro symmetry group. And some subsequent steps in this direction would be connect with the path integral optimization, that is, understand the circuits that I was talking about today as realized by path integrals on curved geometry in quantum field theory. So this is a quantum field theory statement, which were specified by these gradual diffeomorphies f of tau and sigma. After doing this, a natural step would be to connect to path integral optimization and perhaps also to find realization of these circuits as holographic geometries. And the other natural thing that we want to attempt into the future is to perform a detailed comparison with holographic complexity proposals in ADS3. So this is all I had to say. Thank you very much for your attention.
Okay. Thank you very much for your very instructive talk. We had a lot of discussion about complexity, so I expect there are several questions. Please, we are out of time, but still we can spend 10 minutes for questions. Don't hesitate to ask Michael for questions, okay?
Hello, I have a question.
Hi, Johanna.
Hi, Michal. Very nice talk. Yeah, thanks a lot. Just some very quick questions. So I think the main asset of your approach is to use this quadratic cost function of the Fubini-Studi matrix. So as I recall from the Caputa and Magan paper, in the large C limit, actually the linear term becomes dominant if we expand the square root. And then it just becomes linear again. Can you comment on what happens in your case in the large C limit?
I would say that my very superficial answer would be that the large C limit is, I would say that it's a bit subtle. In particular, one should also care probably about the square root here. And what I would expect is that in the large C limit, the square root will lead to a big absolute value that you have to take into account.
Okay, that would be important for holography, of course.
Well, I mean, I'm not sure actually, because I think there are two statements. One statement is about factorization of correlations in the large C, and when you look at our calculation, what we're doing is we're looking at the connected correlator of we're looking at the Fubini study here is based on a connected correlator, right? I mean, like you see it in our definition because we calculate the the 2-point function of a single layer of a circuit and subtract from it the square of the 1-point function, right? So somehow we remove. I think that the statement in Pavel and Javi's paper was based on the observation that if we have just this piece, then it's going to be dominated by this contribution. But in our studies, we remove this contribution, and this contribution is precisely the one that is responsible for this phase that appears there. So in a sense, the large C limit in our case, my claim would be is non-trivial and is not given by what appeared in their paper.
Okay, thank you very much. Thanks for the nice talk.
Thanks.
More questions, please?
Yeah, let me ask right for this question, Michal.
Hi, Johannes.
Hey, so is the Fubini study metric in the Nielsen picture that you've just shown identical to the general definition that you have, or?
Oh, that's a good question. Actually, I was thinking about it yesterday, and I don't really have a good answer to it. I mean, it's structurally identical, but it's for a different variable. It's for an inverse map. So I don't yet know how to get a handle on it. My gut feeling is that it's subtle and that one should be careful, but I don't have a good answer for you. It's a good question. I also thought about it.
And the upper one is really the distance in Hilbert space, and the lower one in Nielsen picture is like kind of an approximation, or
No. So the first statement that you made is correct. It's a distance in Hilbert space that you traverse by following the circuit that we constructed. I mean, it's more general. I mean, you don't have to do this for a CFT. You can do this in other quantum mechanical system. And the second one is just Nielsen. I call it Fubini study Nielsen because what we do is we basically, if you go back to the beginning of my talk, in Nielsen's approach, you have to specify a norm, and this L2 norm comes with a specification of penalty factors, as you know, right? And the only thing that I'm saying is that these penalty factors can originate from a 2-point function of the stress tensor in the state H, and that these seem to be nice penalty factors, and that's the only statement that I'm making. It's a good question. Thanks.
Hi, Michael.
Hi.
Hi, I'm Javier. Yeah, actually, I want to just make a comment. So the Fubini study, we also consider in our paper. It's in an appendix. And our point is not that it vanishes in the large C limit. Of course, there is an action for it, and it's there. It's written there. Our point is that it's proportional to
square root of C.
Square root of C. So yeah, my question is, so for us, I think that is a problem, because when you want to, for example, I mean, there are many problems that you are going to consider in which, for example, the linear growth of complexity with energy, or the volumes, many problems in which, you want to consider actions that are proportional to C. And that's the main reason in our paper we studied that cost function, and we just didn't put it in the first line because of that reason. So I wonder if you can comment.
Yeah. So somehow myself, I'm a bit hesitant about overall normalizations of these things, in the sense that in all these works I was really persistently neglecting this overall normalization factor. So I never really paid attention to this square root of C or C factor appearing in front. I was more interested in looking at what are the optimal circuits. But also, I mean, the reason why I was doing this is that if one looks at least at the volume proposal in holography, then the normalization is also arbitrary, right? You can normalize it in various ways. Of course, you can invoke some other principles to argue for some particular normalization, but I think these principles still leave a lot of freedom, and I'm not sure that they are like fully justified. So I would say that at least on my side, the scaling with C is probably not the thing that I would pay the most attention to. The more important feature is the question of the variational problem. If we can find a solution that interpolates between arbitrary two transformations, and I think Fubini study does have this feature. And also, what I like about Fubini study personally is the fact that the U1 factor it automatically takes care of. Because you subtract it via this difference between, like in the variance. But
I want to comment about that. I want to comment that in our action you can also interpolate between any 2 points. It is not true that you cannot, because that's the actual definition of so the coadjoint orbit is a homogeneous space, and you can interpolate between any 2 points. There are trajectories always. And so there is no, I don't see, I mean, that criticism that maybe, I don't know if it arises by Johanna's paper, but that criticism is completely, I don't think it's correct. It's fully, it is misleading.
Well, I mean, I would say that my natural gut feeling is that when you think about this, the actions that are, or like the expressions that are first ordering derivatives, these expressions allow you to specify, I mean, if they have a standard initial value problem, then if you specify the function at any point of your circuit or of this procedure, then it defines what's the function at a later instance, right? So that's why I want to have two derivatives. Because
we have two derivatives. We have two derivatives. It is just when you approximate. It is just when you approximate that it is like one derivative, but you have two derivatives. It is the expectation value of the stress tensor square, and there are two derivatives.
Well, I'm like,
and when you see the problem in the geometric action perspective, you can just think about it as seeing. It's not a first order formalism, a trivial first order formalism. It's just like a Hamiltonian formalism, in which you specify first derivatives because I mean, it's a first order formalism, but it's not a bad post variational problem.
Well, I mean, like the instant. Well, I think we should probably stop this discussion at some point, but we should discuss the 2 or 3 or 4 of us at some point. I mean, like the instance in which I see first order equations are in the context of using the time coordinate as a null coordinate, right? But then things are a bit subtle. So like that's probably the only way out from this conundrum that we only have one derivative in some action.
Okay, maybe you are right. We have to stop with discussion. If there is just one urgent question, please ask.
I have a very short question.
Yes.
So is it possible to study the definition of complexity in the dynamical situation, like in quenches or something like this? This is very popular for entanglement, and here, does it make sense?
Yes, of course. I mean, that's an excellent question. I should probably mention this more carefully. So, you know, for quenches, what you do is you generate a time-dependent state, but it's a state in Hilbert space that evolves in some particular way. And at every instance of time evolution, you can ask a question: what's the simplest way to obtain the state that you have at a given instance of time from, say, your ground state or some other state that you choose to be the simple one? It's a well-defined question that you can try to answer. And in particular, in this paper 1807, with Hugo Camargo, Pablo Zaputa, Rod Jefferson, and and Diptar Kadas, we looked precisely into that sort of a question for free quantum field theories. And I know that people looked at these holographic complexity proposals for quenches, and they made their own predictions. So it's a very good question.
Right. In pre-QFT, it is it was done, but I mean, in this new definition by coadjoint orbits and other stuff.
Oh,
I mean, in this way.
I'm not sure. I don't really know. But yeah, I mean, if somebody has an answer, please provide. I mean, my gut feeling would be that yes, it will be possible in some limited way.
Okay, maybe it's a time to thank Mike once again for very instructive talk. Thank you very much.
Thank you.